Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through three-phase circuits. In our previous lessons, we've gone through power in AC and alternating circuit generation, waveforms, and the others. So if this is the first time you are visiting us in this channel, kindly subscribe so that you get access to all the previous videos. Okay, so three-phase circuits. Now, in our previous lessons, all that we've been doing is what we call single phase, okay? All that we've been doing is what we call single phase. Single. So we learned that an AC alternating circuit has a pulsating current or voltage, right? So you have a rising phase, it falls down to zero, then it goes back to the negative and comes back. So we call this pulsating, right? So it goes on and off in that manner. Now, when you have bigger machines and you have heavy duty machines, you want to power a very complex system, you can't use a single phase which is pulsating to power such a system. Some systems require huge amount of energy, right? So here, how do we continuously produce energy to that system whilst you are trying to compensate the pulsating nature of this? So you realize that if you have just a single track which is feeding, let's say you have a farm here, right? You have a farm, so there is a farm, then we have our market here, right? So the market centers are here. You realize that if you have only one track which is trying to convey goods between these two, right, you realize that this will have to go several times in order to achieve a particular goal. But what if we have three tracks? So if we have three tracks, you have one which is going, the other is also returning here, right? Then you have another one probably also going. So you realize that the work that this one is going to do, which will take a lot of time, then these three tracks are going to make it a little bit easier. I'm just trying to let you appreciate the concept of three phase circuit and why it is important. So due to the limitation of a single phase system, if you have transmission lines and you want to convey large power, right, from let's say Akosombo Dam to your homes, then it means that you need to use a very thick copper wire, right? So in the transmission, it will require a very large current for you to convey that power through. So it will require a very thicker copper wire, which will means that you need to spend a lot of money because materials are very expensive, right? Also, there will be heat and a lot of factors, right? Now, what if this same quantity of power I can split it into three and contribute it by maybe three wires? So here I can get three thinner wires which will rather perform the same function. Okay, so here three-phase system is here to save us the cost, save us the flexibility. And the interesting part of three-phase circuits is you can even get a single phase out of it. So if you want to power a fan or a television which requires just a single phase, you just tap, then you just use. If you need a very heavy duty machine that requires a huge power, then you use a three-phase. Now let's go straight to three-phase system. When you talk about a three-phase system has two components, okay? So a three-phase system has two components. We have the first component to be what we call three-phase generator. You have the generator, then you have what you call the three-phase load. Three-phase load. So the generator is to produce our voltage and also convey the current. Then the loads here are the resistors for controlling, or it may be a resistor, it may be a television, maybe whatever, right? So there are two ends. So that is these two things, the generator and the load come together to call what you call the three-phase system. Okay, three-phase system. So it comprises load and generator. Now, in three-phase system here, we want to use what you call phase, right? So the application of phasor diagrams here helps us to appreciate three phase very well. So a power supply system consisting of the voltages which are 120 degrees out of phase, okay, is what we call three phase system. If I draw any system like this, or like this, or let me use a simple star approach to make you understand it well. Yeah, like this. You realize that this first one, let's say, let me make it B1. Realize that it is straight, so I'll give it B0. It doesn't have any. I mean, I'm going to use this as a reference, right? You realize that this one, I can see that the angle between this is 120. So the voltage here is V2 angle 120 negative. And I can make this V3 angle 1 positive 120. So if you have three separate branches like this separated at 120, each conveying current to a system, then our idea is that at any point there will be continuous flow of current. Okay, so this is the whole thing of three phase. So this one is exactly delta star transformation we did in the resistors. Okay, this is where we are applying to supply and also use voltages and current over a transmission line. There are two main there are two main configurations for three phase system. So now let's consider the three phase system. So the first one we have is what we call the delta, and we have what we call the star configuration. Okay, so let's understand what star and delta configuration are. With the delta configuration, as usual, I'll have this in the triangular form, right? Like this. And I'll have this, have this, have this. So I'll call this line 1, line 2, line 3, right? And I'll also have my V, my V, my V, my direction showing here. I'll come this way powerful, right? Then let me do that for my star. So with the star configuration, obviously you know I'll have this, I have this, I'll have this, I'll have this, right? And my lines will come in. With my lines coming in, one here, one here, and one here. I'll have L1, L2, L3. Now there is this significant difference between the delta and star configuration. It's what we call the N, neutral point. Neutral point. Okay. So take note of that. You're going to talk about that very soon. So let me label this as VA, VB, then my V. Right. So I'll have my voltage. This coming this way. Coming this. Now, per this two description I have here, I believe you clearly understand that there are some features. You see L, then you see V, right? So we have what you call phase. These are some few terms you will understand. A phase, and you have what you call a line. So imagine the poles you see in your various home. If you see the pole like this standing there, you realize that it has got these three wires. Some has got four wires, right? So you get to understand all of them in the course of this particular section. Okay. So in the course of three phase circuits, I'll take you through the four lines and the three lines. Okay. So a line is connecting pieces together. Okay. So if I have this line here, you realize that these poles are connected together. Each line will have a corresponding what piece to connect to. Okay. So we have what you call line voltage, and we have what you call the phase voltage. Okay. Remember that we have three phased system which we are combining to give one thing, but each of these phases are connected to lines, and the lines are what we call the line voltage. So the voltage across a line is a line voltage, and the voltage across a particular phase is the phase voltage. These are some terms you'll be experiencing. One key thing about star is that a star has a neutral point, and that gives it a very special feature. All generators are in star configuration, every generator. So please take note of that. Sometimes a question may just say that yes, a generator this without telling you that it's a star or delta. Please take note that it is a star configuration. Okay. So one important thing you have to also learn is that, so here you can see that my VA, so I can say that my VA, right, is equal to VM sine omega t. My VB will be equal to VM sine omega t plus 120 degrees. Sorry, that's my VB, right? It should be minus. So the B becomes minus. So WT minus. Then the VC then becomes VM, sorry, sine omega t plus 120. So these here are the hot representation of the respective phase voltages. Okay. Now let's understand the relationship between a line and a phase voltage. So as I explained that we have a line and we have a phase. For us to really explain this very well, I think we can use the same configuration to explain that when you have a delta, what is the relationship between its line and phase voltages? So let's see that quickly. Okay, so for a delta configuration, we don't have any neutral point. Okay, you realize that the voltage across any phase and any phase is the same voltage that will be across the lines. Is one key thing that you have to know. So for every delta configuration, okay, say that line voltage is always equal to phase voltage. It's something you should know. Line voltage is always equal to phase voltage. Why? Because it doesn't have what? A neutral point. So here, what do? You say VL is equal to VP. One key formula for you to keep it, because as we move forward, you'll be using this formula a lot. What about the current designation? So with the relationship between the current two, now when you come to the currents here, the currents within a phase and the current within a line. So we have a current in these three lines, right? We have the current within a phase, right? So we realize that there are nodes here. Is that not it? You can see clearly there are nodes at each point. Is that not it? Yes. So mathematically and proving, we see that the phase we say that the phase current, okay, the phase current IP of a delta configuration of a three phase is always equal to the line current over square root of 3. The line current over square root of 3. So here we assume that there will be current in each branch, right? For it to emerge from the L, right, it is going to be a simplification, and that has been simplified to give this formula. So for your understanding, just keep these formulas in mind. There are some key formulas you have to know. So in any delta configuration, you know that my line voltage is equal to my phase voltage ticked. My line current is equal to my phase current times root 3, or I'll say that my phase current is equal to my line current over root 3. That is also ticked, right? Now let's come to the star configuration. With the star configuration, you realize that there is a powerful node here, and this node help us to tap single phases. So you realize that if I tap from here, this is my neutral. Okay, if I tap from my neutral and I tap from my line 1, what am I getting? I'm getting a single phase where I'll have VAN, that is my voltage on the line 1 and my neutral that can be supplied to a home for that home to use. So if I've observed, there are some special smaller light poles around neighborhood where these poles have two wires. One wire is carrying the actual voltage line and the other is neutral. So I can tap three different single phases from a star configuration. That is one key feature of star. But let's check something. You realize that the current across this phase. So if I have this phase, the current across this phase is the same as the current that will pass through the line. That is one clear thing. So for every star configuration, my phase current is equal to my phase, my line voltage. Take note, equal to my line current. That's the first thing. This one you should know, that the same current that is flowing through a particular phase will be the same current that will pass through the line. So we say that your IP is equal to your IL in any star, while that is the opposite in the delta. Similarly, what about the voltage? If I want a voltage across this, and I want to know the voltage across this, right? So I want to, the presence of this node here affects the voltage distribution. So the voltages across each phase will not be equal to the voltages across each line. Take note. The voltages across each phase wouldn't be the same as the voltages across each line. And mostly in series connection, the voltages are a little bit what different because there is a voltage division. So here, without going through the formulas proving again, you conclude that our VP will be equal to VL over square root of 3. As simple as that. So I believe that you should understand the relationships appropriately, that in a star configuration, your line current is equal to your phase current, by your phase voltage will be equal to your line voltage over square root of 3. So keep this and let's solve a couple of problems for you to appreciate this very well. Okay. So our example one, first example, right? So I have three identical connected star across a three-phase 450-volt supply. If each resistor has oh, so if each resistor has a resistance of 50 ohm, calculate A. I need the voltage across each resistor. B. The current in each resistor. And finally C. The total power supplied to the load. So this example, three identical resistors are connected in star across a three-phase 415-volt supply. If each resistor has a resistance of 50 ohm, calculate the voltage across each resistor, then the current in each resistor, the total power supplied to the load. So let's go straight solving this problem. The solution. So to solve this problem, the first thing to do is identify which configuration you are going to work with. So from the question, you are going to deal with star configuration. So with your star configuration, you design something somewhere, right? Then you have your lines, have your neutral, line 2 and line 3. Then you state the formulas. Remember that whenever you have a star configuration, what do you know? Know that my IP is equal to my IL. My line current is the same as my line, my phase current. Then number two, my VP is equal to my VL over square root of 3. Once you have this written down, you are done. You come down to extract your data from the information given. From the information given, I was given 415 V supply. That is your total voltage. But wait, this is a star configuration. Is that not it? For a star configuration, if I have my line, so whenever they tell you that a three-phase supply, the supply here means that this is what is coming out of your generator. These are some key terms you have to take note. Supply is what is coming out of your generator. So if supply is what is coming out of your generator, then it means that that's going to be your line voltage. That will be your line voltage. So then you simply extract. So extracting my keywords, I have my VL to be equal to 450 volts. Write it down. What is my resistance? He said each resistor. So each particular phase has a resistance of what? 50 ohm. Therefore, my ZP, which is impedance across phase, is 50 ohm. You have written this one to down. Then we come to the question: what do we need? What do we need? We need a voltage across each resistor. So we need VP. That is each phase. We don't know. Number two, we need current in each resistor. We need IP. And number three, what do we need? We need the total power, right? Total power. So now let's solve this and see. So since I have extracted my values to calculate the voltage across each resistor, that is what we call the VP. You know that this is a star connection. In a star connection, my VP is simply equal to my VL over square root of 3 as I listed here. Therefore, I'm going to have 400 and I'm going to have 415 over square root of 3, right? 415 over square root of 3. So what's the answer for 400 over square root of 3? This gives me 240 volts. Okay. Then I come to my B. So with my B, I have, he said current in each resistor. So I mean that is your phase, okay? You realize that each resistor is on a particular phase. So your IP is going to give us my IL over root 3, right? This is going to give me, now, do I know my IL? That's the question you ask yourself. So now, how do you find my IL? But do you think, I don't think we can find the IL, right? So we know that the voltage across each, remember this VP is a voltage across each resistance. That is VP. And that is 200 and what? 40 volts. I know my resistance across each phase to be 50 ohm. Therefore, to find my IP, I can change it from IL simply by finding my VP over my R. This is as simple as possible, right? So your phase voltage over your particular impedance across that phase, which is now 240 over 50. That gives us 4.8 amperes currently. Let's go to the C. With the C, we have the power. So we should calculate the power in this three-phase system. To find the power in each phase. Is a balance system. We have equal impedances, so the power is finding the power in one phase and multiplying it by 3. As simple as that. So my total power is simply equal to 3 times my phase power, and that is going to give me 3 times, what is my phase power? My phase power is simply IV, if you know that, right? And phase power is what? IV. You know, IP times what? VP. That is all. So what is my 3 times my IP? My IP is what? 4.8 times my phase voltage is 240. As simple as that. This gives us what? 3, 4, 5, 6 watts. As simple as that. So you can see, three-phase system is not difficult. Extract your information, solve what the question is asking you to solve, and that is all. Right. Now let's quickly solve example 2. For example 2, we said 3 identical. So you realize that these questions you are solving are identical. You do sections where you don't have a balance impedances. So 3 identical impedances. are connected in delta across a three-phase 415 volts supply. If the line current is 10 ampere, calculate A, the current in each impedance, B, the value of each impedance. Right. So we said three identical impedances are connected in delta. That is what I want you to take note. So I said whenever they give a question, identify the configuration. That's the first step. So we have delta. So in delta, as part of our solution, you realize that in delta, our phase voltage is equal to our phase current. Is equal to our phase voltage, our line voltage. Then our phase current is equal to our line current over square root of 3. You lay this down, it will guide you. Then the second thing is, we have 415 supply. I said when you hear supply, it means your line voltage. So my VL from the question is simply equal to 415 volts. You put it down. Now what do we need again? If the line current, now we have line current, that is what? IL. Let me use yellow. So if IL is equal to 10 amps, what do we need? Calculate the current in each impedance. So we need IP. We don't know. Then the value of each impedance. We need ZP. We don't know. So here, first of all, how do you find IP? You know the formula that IP is always equal to what? Your, in this delta, right? So IP is equal to your IL over square root of 3. And this gives me 10 over square root of 3, giving me 5.78 amperes. Then I'm done. I need a value for each impedance. The value for each impedance is simply equal to my ZP is simply equal to my um voltage across that phase over the current across that phase. Is that not it? This is Ohm's law. It doesn't change. The Z here is just your resistance, right? So my phase voltage, remember that in a delta, your VL is equal to your VP. So I still get 415 here over my IP, which is now what 5.78. As simple as that. And this gives me 701.80 ohms. As simple as that. Yes. So this is how we handle questions. It's so easy. It's not difficult a bit. It's not difficult a bit. So thank you for being with me in this lesson. I'll see you in the next lesson as we do the power in three-phase system, how to calculate power, and we solve more example along the line. See you.